Welcome to this video on bijective proof. In a bijective proof, we construct a bijective mapping between two families and then conclude that the families have the same size. There are two phases in a bijective proof. First, you have to come up with the mapping. Sometimes this is easy, and sometimes this is quite hard. In the second phase, you must rigorously prove that your mapping is a bijection. So let's get started. This slide collects some of the ideas from the previous video on bijections. I do want to note that we truly need the rigorous definitions from that video, but here I'm going to give an intuitive summary. Let's start with injective, surjective, and bijective. We have a function f that maps from a finite set x to a finite set y. This function is injective, or one-to-one, when every element in the set y is mapped to by at most one element in the set x. This function is surjective, or onto, when every element in the set y is mapped to by at least one element in x. And finally, the function is bijective, when it is both injective and surjective. This means that every element in the set y is mapped to by exactly one element in the set x. We have a second way to characterize bijective functions. The function f is bijective when it has an inverse function, that is the reversal of the function f. This means that two properties hold. First, applying f and then g gets you back to where you started in the set x. Second, applying g and then f gets you back to where you started in set y. Both of these conditions have to hold for g to be the inverse of f. Now we are ready to describe what a bijective proof is. We have two sets, x and y, and we want to show that they have the same size. We will do so by constructing a bijection between them. We have to do two things. First, we construct a function that we believe to be a bijection. Then we have to actually argue that that function is a bijection, either by showing that it is injective and surjective, or by constructing an inverse function. Either one of these approaches is equally good. In fact, you end up having to explain the same phenomena in both cases, so it's really just a matter of style. You'll find that there are some problems where it is easier to explain injective and surjective, and there are some problems where making an inverse function argument flows more easily. So you should just trust your instincts and try one way. If it doesn't go so well, then try adapting your argument for the other way. Here's our first example of a bijective proof. We have two sets that we want to show have the same size. The first is the collection of all possible subsets of the set of size n. This is called the power set of n. Our second set is the collection of all binary words of length n. To create a binary word of length n, we just create a list of zeros and ones. For example, I've listed all of the subsets of the set 1, 2, 3, and I've listed all the binary words of length 3. The order in which I've listed each set actually corresponds to the mapping that I'm going to use between them. Given a subset, I set the kth value in the corresponding word to be 1 if the number k is in the subset, and 0 if it is not. For example, the set 1, 3 maps to the word 1, 0, 1. This mapping is reversible. Starting from the word, I create the corresponding set by adding the number k to the set if and only if wk is equal to 1. For example, the word 0, 1, 0 maps to the set 2. Here is a sketch of what the proof should look like. And note that while I looked at the particular value n equals 3 on the previous slide, I've written this proof for a generic value of n. So here we go. I define a function f from the power set to the set of binary words. You can see that my description here matches the explanation I gave on the last slide. W sub k is equal to 1 precisely when k is in the set S. Next, I define the candidate inverse function g. This goes from binary words to subsets of n. That subset contains the element k precisely when wk is equal to 1. So there is more to do. I now need to argue that these two functions really are inverse functions. That is, I need to show that if I start with a set S and apply the function f, and then apply the function g, I get back to the same set S that I started at. And I need to show that if I start with a binary word w, apply g, and then apply f, I get back to that same binary word that I started with. These two arguments are pretty straightforward for these simple functions. Okay, so let's look at a trickier example. My first set, a sub n, is the collection of subsets of 1 through n that do not contain successive elements. That means that if 3 is in my subset, then I can't have either 2 or 4 in the subset. And here are the 8 subsets that appear in a sub 4. The second set, b sub n, is the ways to write the integer n as the ordered sum of 1s and 2s. And here are the 8 different sums in b sub 5. And note that the order of these numbers matter. The sum 2 plus 1 plus 1 plus 1 is different than 1 plus 1 plus 2 plus 1. So our job is to show that a sub n is in bijection with b sub n plus 1. This problem is quite a head scratcher. If we were encountering this problem for the first time, what we would have to do is look at some examples. Here I've shown you a4 and b5. Maybe we would have to look at a5 and b6 and a7 and b8 and so on. We would then look for patterns and try to guess what the mapping is. But in this video, I have a more limited goal. I just want to show you what a bijective proof looks like. So I'm going to reveal the mapping and then argue that it's correct. As in the previous example, I have listed the two sets so that the rows correspond to my mapping. And so here is how I'm going to get from b5 to a4. First, I will replace the sums with an equivalent structure, a list of boxes of widths 1 and 2. And here the width 2 boxes are gray so that you can see them a little better. Next, I will write the numbers 1, 2, 3, 4 above the first 4 positions of these boxes. Whenever I see a gray box of width 2, I will write the number that corresponds to its first position. I don't write anything in the white boxes of width 1. In other words, a width 1 box means skip this number, and a width 2 box means take the first number in the box. Now, I just take my set to be the numbers that I wrote in my gray boxes. Now that we understand the mapping, here is a sketch of the proof. If I were writing this up, then I would need to fill in the details. Instead, I'm going to have you add those details in the you try problem for the video. I start by defining a function that takes me from bn plus 1 to a sub n. Given an ordered sum of 1s and 2s that add to n plus 1, I draw the corresponding boxes of width 1 and 2. Next, I create a set S. If k is at the start of a box of width 2, then I add k to the set S. Now, I have to do 3 things. First, I must show that my mapping is well defined. This means that I must confirm that the set I created really is in a sub n. So I have to argue why the set S does not have any successive elements. Next, I must show that the mapping is injective. Given 2 different ordered sums, argue that they map to different sets. Finally, I must show that the mapping is surjective. Given a target set S, I need to find an ordered sum that maps to it. This is where you take over. I want you to fill in the details in this second example. On this final slide, I have given you a hint for each of the 3 parts. You should be able to answer each of them using 2 or 3 sentences. Do the best you can. Good luck, and have fun.